That right? So we learned the bisection method and we learned the regular falsy method. So in that actually the third one is the Newton-Raphson method. So this is also called as Newton iterative method. So this is the thing actually what we are going to discuss. So in this, right, the convergence is very fast. That is the most advantage of this Newton-Raphson method. But actually this is a great advantage. It's not a simple advantage, right? So we take actually earlier actually in the bisectional method and the regular falsy method, if you notice, we have done actually at least 8 to 9 iterations minimum to get to the solution. But actually here in Newton-Raphson method, you will be getting the solution within 4 or 5 iterations itself. And that too actually if you are assuming a closer solution, then it might take even lesser number of iterations to get into the solution. So that is, suppose if the function f of x is equal to 0, and then for this actually we wanted to identify the solution. Now the origin of this Newton-Raphson method comes from the Taylor's expansion. So the Taylor's expansion, what it says is f of x plus h is equal to f of x plus h into f dash of x plus h square by 2 factorial into f double dash of x plus h cube by 3 factorial into f triple dash of x plus dash 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 up to infinity. So this is the Taylor's expansion. So this Taylor's expansion actually comes from the mean value theorems in calculus, right? So from the mean value theorems you are going to get this Taylor's expansion, and from the Taylor's expansion you are going to get the Maclaurin series, and Maclaurin series actually is one of the powerful tool to convert any random nonlinear function into a polynomial, right? So that is the advantage of the Maclaurin series. Now here, when you are able to express f of x plus h, where x is the point where we are considering, and the functional value at a deviation of h from the x, so the functional value you will be able to calculate in terms of h and f of x. So that means here actually, let us say this is a function. So let us say this is the y is equal to f of x function. Now this function value, if you consider that at this particular location, or I call from this side, so this is at x is equal to x naught, and then here f of x naught value, so this function value is nothing but y is equal to f of x naught. This is the functional value. But actually there is a distance of h from this location where you can get the solution. So this is the h value. Now if f of x plus h is equal to 0, f of x plus h equal to 0, then this is going to the solution of this ideal equation f of x, right? Where the solution is located at a distance of h from the x naught. So from this understanding actually we will derive the Newton-Raphson method. So f of x naught plus h equal to 0. If f of x naught plus h equal to 0, then let x naught be the first approximated solution. So x naught be the first approximated solution, which essentially means that this is the preliminary guess of ours, where you are trying to locate the solution as at a location of x is equal to x naught. But ideally this is located at a distance of h from x naught. Now it is time to calculate the value of h, where you can get the solution of the function, where this value f of x naught plus h, so this is the value where it is becoming 0. Now here from the Taylor's expansion, if you write for x naught, then f of x naught plus h equal to f of x naught plus h into f dash of x naught plus h square by 2 factorial into f double dash of x naught plus dash 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 up to infinity. So this is the Taylor's expansion which was written for the function at x is equal to x naught. Now, once you identify this location, then actually we know that actually the solution is occurring at a distance of x naught plus h, which essentially means that the function value is becoming 0 there. So if this is becoming 0, then if you try to approach, so as h is smaller, neglecting the higher order powers, of h, then so 0 equal to f of x naught plus h is equal to f of x naught plus h into f dash of x naught, and then you can neglect the higher order terms. From there you will be able to calculate the h value is equal to minus f of x naught divided by f dash of x naught. Now this h value is an approximated root of the original function f of x. So this is located at a distance of x. So this is the second approximation where x1 is equal to x naught plus h is the second approximation. And from there actually you will get x1, then from there you can calculate x2 is equal to x1 plus h again. And then this h value is the third approximation. So like this actually you can keep on approximate so that actually you will try to reach the location of the root ideally. Got it? So this way if you try to converge to the solution, then actually the convergence is very, very fast. Got it? Okay. First you note down this, then actually we will try to see what we are trying to approximate here with the help of the tangents. So with the help of this Norton-Raphson method, so you will be able to find the nearest root by adding h value which can be calculated from f of x by f dash of x. So initial guess is x naught, and first approximation x1 equal to x naught minus f of x naught divided by f dash of x naught. And then the second approximation x2 equal to x1 minus f of x1 divided by f dash of x1. So like this actually you can keep on try to locate this particular root. Now here it is, if you notice, let us say I have considered the point actually x is equal to x naught, and then this location the coordinates are x naught comma f of x naught. So x naught comma f of x naught. Let the slope at this point is going to be f dash of x naught is the slope. So with this slope from this particular point, if a straight line passes through, then that straight line is nothing but the tangent of this. So this is the tangent which is located at this particular point where x is equal to x naught and y is equal to f of x naught. Now if you try to find out the equation of this tangent, and this tangent equation is going to be y minus y1, y1 is f of x naught is equal to slope is f dash of x naught into x minus x naught. So this is the equation of the tangent. So if this is the equation of the tangent, then actually, so I can write this value as the point where this tangent cuts the x-axis is at y equal to 0. So that means the y coordinate is going to be 0 from the place where this is cutting the x-axis. That means this is the location. So at this location, y is going to be 0. If you substitute here, 0 minus f of x naught is equal to f dash of x naught into x minus x naught. Now the location where it cuts the y-axis is going to be x is equal to x naught minus f of x naught divided by f dash of x naught. Now this is what essentially the Newton-Raphson method talks about. So earlier actually we tried identifying two different points, either it may be in bisection method or in the regular falsy method. So there actually you will be identifying two different points where the function value is one is negative, another is positive, and in bisection method you have taken the average of these two and then try to get the next approximation. But in regular falsy method, for the two different points, you tried getting the straight line equation. That is, suppose if you identify this as one point, then this is the straight line actually. You tried drawing it, and then for that actually you found the equation and tried locating the where it cuts the x-axis. And that value actually we have taken as the next approximation. And from there actually we tried approximating to the nearest value. Now here actually in case of Newton-Raphson method, rather than identifying this straight line equation, just a minute, I'm getting a call. Yeah, sorry. So here actually, rather than finding this straight line equation, we have taken only one point rather than 2 points. Unlike in bisection method and regular falsy method, we have identified two different points. Now here actually we have identified a single point or the single value. From there actually we are trying to approximate the nearest root. That point is x is equal to x naught. Now there actually you tried finding the straight line equation because you know the slope as f dash of x naught at that particular point. So as you know the function value, you will be able to calculate the derivative as well. Hence you will be able to know the slope of the tangent at that particular point. Now being known the tangent slope and the point, you will be able to find out the straight line equation, which is nothing but the tangent equation. That tangent equation you tried identifying the location where it cuts the y-axis, and that y-axis value we have taken as the next approximation. So suppose if I draw this equation like this, then actually initially this is the initial guess, and from here actually you tried drawing a tangent like this, and this is the next guess, and then actually you tried identifying this function value exactly the same way what we have done in case of regular falsy method. There actually we tried identifying one more straight line equation. Now here also we do that one more straight line equation, but it is of the tangent equation. So then actually you tried drawing this tangent equation. Now actually it is very closer. So within 2-3 steps actually you will be able to reach almost closer to the root value where it crosses, this function crosses the x-axis. So there actually you will be able to arrive immediately. Otherwise actually you will take one more approximation and try to draw the tangent there. So this is straight away the solution of that equation. Got it? So like this actually very fastly you will be able to converge, and this convergence is very, very fast if the slope when it crosses the x-axis is almost infinite. Why? Because if it is very closer, like so this is almost like vertical, when it crosses, then actually tangent will be converging very fast to the solution. But actually if it is not, suppose if you try to take this equation which is almost parallel to the x-axis, then suppose if this is the first approximation, then this is one approximation, and then this is another approximation, and this is another approximation. Like this actually it may take more number of steps if the slope of the curve at the point where it crosses the x-axis is less. Got it? So this is the characteristic of Newton-Raphson method. So that depends on the slope when it is crossing the x-axis. If it is more, then you will be able to converge to the solution very fastly. If it is less, then it might take more number of iterations. But so nevertheless, this is always a better method when compared to regular falsy method or bisection method. Got it? Understood? So you are trying to approximate as a tangent. Earlier actually we tried identifying just two different points and then try to identify the straight line equation, which is the place where it cuts the x-axis is the next approximated route. Rather than that, now here it is a tangent equation where it cuts the x-axis. That's all. That's the only difference. But the procedure actually it came from the expansion of the Taylor. See this. How many iterations, right? So that depends on the accuracy what we need. Now actually in the problem statement actually he will be clearly specifying. So with 3 digits after the decimal. So that is actually when you try to do the iterations, what happens is, suppose you have got the solution as, let us say you have got 3.0426. In the next iteration, let us say you have got 3.0428. And then actually in the next point, 3.0428 again. And in the next one also 3.0428. That means this is keep on repeating again and again. Now there you have to stop. Got it? So number of iterations actually you don't put any count. So you might go actually maybe 3 iterations itself, or you might go 10 iterations, or you might go 20 iterations, or maybe 100 iterations also when we are running the computer programs. But that is always actually there has to be a cross check where you have to stop. That cross check is when the root is continuously repeating the same number after 3 decimals, then you can stop there. That depends on the accuracy. So if you ask for only 2 decimals after the decimal, so 2 digits after the decimal, then if it is repeating 4 to again, so 04, 04, 04 like that actually, if it is repeating, you can stop there. So here actually the number of iterations count actually there is no limit. There actually the way you need to stop the iteration process is, that depends on the accuracy. But suppose if it is a non-convergent solution, then actually you might go for, in calculations actually in our examination you might maximum go of 10 iterations. But actually after that actually you cannot afford to take many iterations from there. But in computers actually usually we fix 100 as an iteration count. After that actually if it's still not convergent, then we stop and we say that the solution is not convergent there. Got it? Usually it will converge. So it depends on the error. So if 042 and 042 it keeps on repeats, then there is no error from the previous iteration. Hence you can stop there. Yeah. So note it down. Note down on problem. Find the positive root of x power 4 minus x equal to 10. X power 4 minus x equal to 10. Correct to 3 decimal places. Correct to 3 decimal places using Newton-Raphson method. Now here the function is f of x equal to x power 4 minus x minus 10 equal to 0. First you have to express in the form of f of x equal to 0. Then once we express into this format, then as per the Newton iterative method, so the next approximation. So first actually you have to identify an approximate solution. So let us consider f of 1. So f of 1 is going to be 1 minus 1 minus 10. This is equal to minus 10. And then f of 2 equal to, so 2 power 4 minus 2 minus 10. So this is almost coming out to be 16 minus 12. So this is 4. Now actually you can approximate this as one of the closest root. That means, so you are getting actually minus 10 to 4 for a change of 1 to 2. So you can start approximating at x is equal to 2. So let the approximated root be x is equal to 2. Then by NR method, x1 is equal to x naught minus f of x naught divided by f dash of x naught. So x naught is 2 minus f dash of x you can calculate from here itself. F dash of x is equal to 4x cube minus 1. So this is, first you will identify this function value, that is x naught minus f of x naught. F of x naught is x naught power 4 minus x naught minus 10 divided by f dash of x naught, that is 4 times of x naught cube minus 1. So then actually you can start substituting the value. So x1 is equal to 2 minus 2 power 4 minus 2 minus 10 divided by 4 into 2 cube minus 1. So you have to calculate this value and then find out the value. Here. Got it? See how 2 is taken. So here actually, here actually 2 is actually, it's not a hard and fast rule. So you can take any random route. But only thing is, try to assure that a value which is closer to f of x is equal to 0. That means here actually if I take f of 1, then actually I got a value of minus 10. If I take f of 2, I got a value of 4. Now if I notice actually if I try to draw the graph, so this is how it is. Now here at x is equal to 1, I got a value of minus 10. And at x is equal to 2, I got a value of plus 4. Now if you notice, here actually this is closer and this is further, right? Sorry, this function value is almost closer to 0 than when we compare from minus 10 to 0. So this is the height and this is the height here. So you can select this x is equal to 2 as a better approximation as the function value is low when compared to minus 10 or which is closer to this x-axis. So you are trying to approach the value which is close or which makes, so the value of x which will make the y value to 0. So you have to identify a value which is closer to this. Now actually rather than selecting 2, you can even try to check one more value. Let us say, so x is equal to 2 actually is trying to, x is equal to 2 is trying to make the value which is closer to y-axis, which is closer to x-axis. Now here actually I can take x is equal to 1.8 and then I can try to verify whether I can get a value which is closer than 4. That means if I get f of x which is x is equal to 1.8, then if I get a value of f of 1, then I can take x is equal to 1.8 is a better approximation where I can start with rather than 2. Got it? But actually even if you take 2 or even if you take 3 or even if you take 1.8 or 1.5 or 1, right? So the number of iterations may here and there actually a little bit more, but actually more or less you will try to approach the same route. But the number of iterations may be, so if you try to approximate as 1.8 as the first iteration, then you may get answer within 2 iterations itself or 3 iterations itself. But if you take, let us say if you take minus 1 as the approximated route, then you might take 5-6 iterations to come to this route. Suppose actually if you take x is equal to 100 as one of the closed route, then still there is a possibility that you can get the route, but the number of iterations may be 20. Got it? But there one caution is there. Suppose actually this curve actually is this way, then actually suppose if you are here, then actually there is a possibility that you can land up at this solution. But actually if you try to approximate as this route, then actually there is a possibility that you might approximate, you might land at this particular solution rather than this. Now in this case, if you select a value which is far from the solution, so that you will decide based on the y value when you substitute the approximated route. So if it is too far from the solution, then actually if there is a nearby solution to that, you wanted to identify this route, but you tried approximating as the first route at this location, then there is very high possibility that you might land up at this solution rather than this solution. Got it? So that you have to be cautious. So this is also a solution, this is also a solution. So if he asks to find out any one solution, then actually you can select any one solution and still it is a correct answer. But actually if you specifically ask for the positive route or the negative route, then try to identify an approximate route which is closer to the positive route. rather than the negative root. Got it? So here actually you try to check the values 1, 1.5, 1.8, 2, like that. Actually you have to check the initial solution so that you will be able to land at this location. But actually suppose if you check for -1, then there might be a possibility that you can land up at this location where you are getting the negative solution rather than the positive solution there. So that depends on the problem statement. Understood, Ved Prakash? Got it? Okay. So this way actually you can approximate. Now actually in this process actually I have selected x is equal to 2 as an approximated solution. Still I will be able to land at the exact solution. Even if I take 3 also, still there is a possibility that I can get the solution to the same location. Even if I take 5 or 10 also, I can get to this location, but it will take more number of iterations. That's all. Got it? So this way actually you can substitute the value, that is 2 minus 2 power 4 minus 2 minus 10 divided by 4 into 2 cube minus 1. So you have to calculate this value, and then let us say this value is coming out to be, I call this as A. You can calculate with the help of calculator. And then in the next iteration, again come back to the same location. So x2 is equal to A minus f of A divided by f dash of A. Let us say if I calculate this, if I am getting as B, then in the next root x3 is equal to then B minus f of B divided by f dash of B. Now here actually when you try to identify this x value, right, suppose actually if it keep on getting the same value repeatedly, maybe with a minor difference, then actually you may stop the solution depending upon the accuracy you need. So accuracy check actually it has to be fixed, either it may be 2 digits after decimal or 3 digits after decimal, so that you have to fix it, the accuracy, depending upon your convenience. Or usually in the problem statement 90% of the cases they will state that after the decimal 3 digits should be accurate. So that is the kind of statement they put it. Got it? So you can note down this. So this way, if you try to identify the solution, I think it is coming out to be 1.856. So being actually, if you take the initial root as 1.8, then actually there is very high possibility that within 2 iterations you will land up at the solution as x is equal to 1.856. So within 2 iterations you might get it. Rather than if you take 2 as the approximated solution, then you may get within 4 or 5 iterations you will get at the 1.856. Got it? So this is all a guess actually. There is no hard and fast rule. But only thing is actually you have to select a value which is closer to the solution. Closer to the solution you will be able to find out by substituting the value in the function. If it is coming out to be a value which is closer to 0, then you can try to approximate as that root. It shouldn't be negative value or it shouldn't be positive value too far from the x-axis. Got it? Suppose if this value is coming out to be minus 10 and this value is coming out to be 4, then actually 4 is closer to this x-axis rather than this 10. So that's why you selected as x is equal to 2. Clear? Any questions? So you can try your own. I'll give one more. Find the Newton's method. The real root of the equation. Find the real root of the equation. X is equal to cos x plus 1. With NR method. Can you try to solve this? Then, so you can try this on your own. Then note down this. Prove that the iterative formulas for the following In that, to find the value of 1 by n xn plus 1 equal to xn into 2 minus nx. Then xn. And the next one is to find the value of root n xn plus 1 equal to half of xn plus n by xn. One by root n xn plus 1 equal to half of xn plus 1 by nxn. Nth root of kth root of n xn plus 1 equal to 1 by k times of k minus 1 into xn plus n into plus n by x power k minus 1. So these are the formulas with the help of iterative methods if you wanted to find out the value of the function or 1 by n. Suppose actually if you want to find out an approximated value of 1 by 28, let us say, then actually there is an iterative method to find out this value as well. So actually these are actually very much useful when we are manufacturing the calculators. So there actually in the calculators, if you want to find out the values of 1 by 28 or actual root of 10 or whatever it may be, you are going to get the values there. Now actually in a computer actually it cannot do the operations like identifying the prime factors, or especially where it is not a perfect square root or if it is not a perfect root, then actually you have to depend only on the numerical methods. So there actually especially the iterative methods are the only solutions for us to design the calculators. So because the computer can do the repetitive things again and again any number of times, hence actually we will be adapting the iterative methods, especially this Newton-Raphson method and Maclaurin's series. These are the two important formulas actually without which we will not be able to design a computer or a calculator at all for any arithmetic calculations. These are the very two important rules. Now here actually for the iterative method, so we have to prove that to find out the value of 1 by n, where n is any random number, a real number let us say, then for that actually this is the iterative method where you can make use to calculate the value of the next iteration so that you can get an approximated value of 1 by n, where you might notice in the calculator, so after decimal actually it is giving many values. Why? Because it is going through the iterative method rather than the exact solution. Suppose you are expecting a solution of x is equal to 3, but it might land up giving 2.9999. Why? Because it will go with the iterative methods. So here actually this is actually all these formulas actually you can derive with the help of Newton-Raphson method itself. That is, suppose if I take this value, I wanted to identify x is equal to 1 by n. So this value actually I wanted to identify where n is equal to 28 here. Now here this one you can write this function as f of x is equal to x minus 1 by n. So this is the function value where x minus 1 by n is equal to 0. For this actually you wanted to identify the root. Why? Because x is equal to 1 by n is the root. So for that actually if you wanted to identify the root value rather than an integer value which is located as 28 here, you will be identifying this root 1 by 28 value. So that is, you can get x is equal to 1 by n value, maybe somewhere around 1 by 0.28 like that I think it will get, right? Okay. So here 0.02 I think. So x is equal to 1 by n. So x is equal to 1 by n can be written this way. Now as per the Newton-Raphson method, so xn plus 1 is nothing but the previous value xn plus f of xn divided by f dash of xn. So this is the value of the next approximation with the help of Newton-Raphson method. Now this value you will be able to find out f of x and f dash of x. So f dash of x, actually if you want to find out, f dash of x is equal to 1 and f of x is equal to x minus 1 by x. So f of x is equal to x minus 1 by n. Now if you replace these values, so this is xn minus f of xn is xn minus 1 by n divided by f dash of xn is 1. Got it? I think so. Here actually you are getting the same value. So this xn will cancel out 1 by n. But rather than this, right, if you try to approximate this function as in a different manner, that is x is equal to 1 by n or n is equal to 1 by x, or this can be written as f of x is equal to 1 by x minus n. So this way actually you can get a different value, because actually you are trying to put this value as 1 by x rather than x. Here actually you are landing up at the same value where you cannot get the solution. So this way if you try to find out, then xn plus 1 equal to xn minus f of xn is 1 by xn minus n divided by f dash of x. So f dash of x is minus 1 by xn whole square. So this minus minus will go for plus, and then 1 by xn square, it goes to the numerator, then xn plus xn minus n xn square. So this is 2xn, and then you can take out, so xn if you take it, so 2 minus nxn. Yeah, that's all. So this way actually you can identify the function value in the iterative format. Now here actually depending upon this n value, so n is coming out to the numerator, then actually you will be able to easily calculate through the help of iterative methods. So xn is the first approximation, and then n is the given value, which is 28 here, and then you can make use of that value, and again you can go for the next approximation with the help of this calculation. Got it? Similarly, you can calculate for the other one as well. So note it down. Then now to calculate root n, let us say x is equal to root n. So if x is equal to root n, then it implies x square is equal to n. Now if you take one function f of x is equal to x square minus n, then the approximation is going to be xn is equal to xn plus 1 equal to xn minus f of x, that is xn whole square minus n divided by derivative of this is 2 times of xn. So this can be xn minus xn by 2 plus n by 2xn. So this is xn by 2 plus n by 2xn. So if you take 1 by 2 out, then xn plus n by xn, this is the iterative method you can adopt to calculate the value of this function x square minus n, where x square minus n, if it is equal to 0, then the solution of x is going to be, that is xn plus 1, which is the value of root n. So xn plus 1 will give the root n approximately. Got it? Similarly, you can do even for 1 by root n also. So, for 1 by root n also, you can calculate f of x or x equal to 1 by root n. Now, if you square it on either sides, x square equal to 1 by n. So, it implies f of x equal to x square minus 1 by n equal to 0. So, this is the function value. Now, f dash of x is going to be 2x. Now, the approximate root for this is xs n plus 1 is equal to xn minus f of x value is xn square minus 1 by n divided by 2 times of xn. So, this is the function value. So, this is going to be xn minus xn by 2 plus 1 by 2xn. So, this is the value. So, from this actually you can further simplify as xn by 2, which is the xn plus 1 value, plus 1 by 2xn. So, this is, yeah, so you can keep it like this, I think. So, similarly, the nth root also you can find exactly in the similar manner. Yeah, so, nth root also you can find it out. So, x is equal to kth root of n. If you take a power x power k on either side, this is going to be n, then f of x can be treated as x power k minus n, and then this is going to be 0, and xn plus 1 is going to be xn minus f of xn is going to be x power xn power k minus n divided by derivative of this function is going to be k times of xn power k minus 1. Got it? So, this is going to be k times of xn minus xn power k plus n times of divided by k times of xn power k minus 1. So, this is going to be k minus 1 times of xn power n k plus n whole divided by k into xn power k minus 1. So, this is the function value. So, you can make use of this value to calculate the nth root of the function. Got it? I hope you got a clarity on this. So, if you want to further simplify it, you can still simplify it by dividing this x power k. So, any questions on this? So, this is actually to find out the numerical solutions with the help of Newton-Raphson method. If you want to identify any particular value, so we can make use of these formulas to identify the value. So, you don't need to remember these formulas. You can then and there derive these formulas, or actually while solving the problem itself, you can adapt this procedure to solve the solution. Got it? So, note down one problem based on this understanding. Find the value of 1 by 31. So, find the value of 1 by 31. And the second one is root 5, 1 by root 14, 1 by root 14. And the next one is third root of 24. So these values actually he asked us to find. Now actually I will solve this first one, then you can try the other one with exactly the same procedure. So here actually let x equal to 1 by 31. It implies 1 by x equal to 31. So let f of x is equal to 1 by x minus 31 equal to 0. So f dash of x is equal to minus 1 by x square. And then as per NR method, xn plus 1 is equal to xn minus f of xn divided by f dash of xn. So this is as per the NR method. So xn plus 1 is equal to xn minus f of xn is this one, 1 by xn minus 31 divided by f dash of this is minus 1 by xn square. This minus minus will go, and then xn plus 1 equal to xn plus xn minus 31 by xn square. Minus 31 into xn square. So this is 2 times of xn minus 31 xn square, and then if you take out xn out, 2 times of minus 31 xn. So this is the function value. Now here, so let us try to approximate the initial root. Now we are talking about a value 1 by 30. So 1 by 30 is nothing but approximately. So 1 by 30 is equal to 0.0, and then it is 100 by 3 is approximately 0.03. So this is a first approximation value. So this is being the first approximation, let us say x0. Then if you want to find out the value of x1 is equal to, take the first approximation as 0.03 and try to substitute here 0.03 into 2 minus 31 times of 0.03. So we have to calculate this value. So this value is a better approximation. Let us say you get a value of a here. Then x2 equal to a times of 2 minus 31 into a. So this is going to get the value of b, which is almost closure root. So that closure root, maybe I think it is around 0.03226. So x3 value 0.03226. Now if you notice, we started with an approximation of 0.03, but we landed with a value of 0.03226, which is the exact solution of the equation, which gives the value of 1 by 31, because we have taken the function as f of x is equal to 1 by x minus 31, which essentially means that x is equal to 1 by 31, where this is in the fractional format. So this is in the decimal format. Got it? So this is how actually you can find out the solution for any unknown numerical value. Similarly, the case of root 5. So you can try to take this function x is equal to root 5, and then you can take a square on either sides, x square equal to 5, and the function is going to be f of x is equal to x square minus 5 is equal to 0. So you have to identify a root for this, which will give the solution for us. Got it? I hope you understood this concept. So only thing is, you are guessing the function from the given inputs to identify the root whose solution is nothing but the value whatever is required for us. So exactly in the similar manner, 1 by root 14 also you can calculate by taking that as x, and you can square it on either sides. X square is equal to 1 by 14, and then x square minus 1 by 14 is the function which you can solve for the solution, where you can get the value x is equal to 1 by root 14. Clear? Any questions on this? Any questions? So if there are no other questions, we are going to stop the class for today. In the next class, actually, I'm going to explain the solutions of the simultaneous equations with the help of iterative methods and the matrix methods. Okay, yeah. So that's all for today. Thank you. Good night.